should I go ahead and start? We're 2 after, and no one has joined in the last 20 seconds or so. So
I did.
Yeah, I think you may have been the last one. Okay, let's go ahead and there's another one, but we'll go ahead and start, and we'll just let them catch up. So welcome. My name's John DeGood, and my title is I'm a lecturer at the College of New Jersey. So I worked in embedded system design for most of my career in industry. So I spent almost 42 full years after college working in designing real-time systems. So I did instruments for chemical analysis, I did high performance computing and networking, and then I did some research in computer security that was involving embedded systems. And then I guess it's I'm in my 4th year now at the College of New Jersey. So this is sort of my retirement career. I'm spending as long as my health and my mind stay good, I'm going to spend a few years hopefully at TC&J and pass along some of my knowledge to another generation. So like some of you, I'm sure, my hobbies tend to reflect the same things that I do at school or at work. And so I enjoy computer hacking and enjoy working with embedded systems, little toy computers. So the one I'm going to show you today, I'll hold it up here, and I guess actually that's not going to work, is it? Because it's making it disappear because of the background. Hold on a second. I think I'm gonna have to turn off the background. You're gonna see my ugly bedroom with a bunch of computer stuff piled on my bed that I was using to prepare for this talk today. And so let me turn off the virtual background. None. Okay. So now you should be able, hopefully, yeah. So here's the little board. I'll take off the piece of foam off of the bottom that I'm going to be showing you some demonstrations on today. And so this is the front of it with the components. And then the back side is bare, except that it has, you can probably see a row of pins on each side, which makes it easy for development. You can plug it into a little solderless breadboard and then add other components to the solderless breadboard and create a prototype from this little board. And so I'll talk about that board in particular. So let me go ahead, and I'm going to do relatively few slides, and then the bulk of this is just going to be a demonstration. I have 2 little demonstration programs I'll run on the board, and I'll answer any questions that you might have. Okay, so this is my little talk. And so first of all, I'm going to talk about what is Arduino. So Arduino is 2 separate things. And so when you talk to somebody about Arduino, there's the Arduino hardware, and then there's the Arduino software. So the board that I'm showing you today is not Arduino hardware. It is a completely different category of development board, but it works with the Arduino software environment, as do a number of different development platforms. So the Arduino hardware I wanted to mention briefly first is it's been around for many, many years. It was one of the first low-cost development boards that hobbyists and people in industry also could purchase. And so it's a company. One of the key things is it's open source. So the hardware designs and the software design are completely open. And so they encourage people to take the designs and modify them. So while you can buy Arduino boards directly from the Arduino company, you can also buy Arduino clone boards that cost much less And the Arduino boards that I have, I'm not going to be demoing any of them today, but you know, I'm thrifty, so I bought the clone boards, and they're just inexpensive. You can buy them for a couple of bucks, mail order from China, and they do the same thing as the real Arduino board that you'd be paying closer to $20 for. So these are little single microcontroller boards. The features of them is they have lots of I/O pins. So there's lots of digital input-output pins that you can set to a 1 or a 0. And there's also usually, it varies with the particular chip, but there's usually a number of analog pins. So you can read voltages, you could measure currents, you could output voltages or output currents with a couple of external components. Okay, so the other half of Arduino is the part I'm going to talk about today. Arduino is also an integrated development environment, and because it is designed as open source, it's been greatly extended. So it not only works with the original Arduino hardware designs, but lots and lots of other people piggyback on this nice IDE and have uploaded their own board descriptions to it, and you can develop for all sorts of other hardware platforms on this as well. So features of this that are notable, I think, are that it was developed in Java, and as a result, it's cross-platform. Java, it runs on Windows, it runs on Mac OS, it runs on Linux. So just about any workstation or desktop that you have, you can install the Arduino software environment and do the development. And it looks exactly the same because it's the same Java code on each of those different platforms. And so rather than spend a lot of time pointing out this, I'll wait until we get to the live demo, and then I'll show you how it works. I guess the one thing I will mention now before we get going is I picked this particular screenshot, and this is one of the examples that we'll be using as a little blinking LED on the board. Is every Arduino program consists of two functions. So there's a setup function that runs once when you turn the board on, and it does the initialization. So anything you want to have run one time at power on, you put in setup. And then the other function is called loop, and it is executed over and over and over again. Let's see, I have a chat message. Can we ask questions now, or should we wait until the end? I am happy to accept questions at any time. So if there get to be too many, I'll probably postpone them, but I don't think that'll probably be a problem. So if you want to shout out a question or type something in the chat window, I'll try and answer them as we go along. So the setup is run once, and then the loop function is, after setup completes, it's run repeatedly. It's a function that the Arduino platform calls over and over and over again. And so what this is doing is it's initially turning the LED on, it's waiting 1,000 milliseconds, 1 second, turning the LED off, waiting 1,000 milliseconds. So it's just sitting there and blinking the LED. So after it finishes, it calls the function again, turns it on, waits, turns it off, waits, and then calls the function again. And so Arduino development is, this may look really ridiculously simple, but a surprising number of embedded systems work this way. So some of the simple devices you have in your home, the software in them may be nothing more than just a loop that runs over and over and over again. And so this is a very common idiom for embedded systems. So this is, I just put this out here as an example of a little embedded system that I developed. So this was a commercial board that is a Geiger counter. And so I purchased it, and there's the base board is got the Geiger counter circuitry on it. This long tube that's about 4 inches long is the Geiger-Muller tube that detects the radiation, and it connects with these 2 wires to this terminal strip on the board. And there's about 400 or 500 volts across this tube. And so when a radioactive gamma ray or a hard beta ray penetrates the tube, it ionizes the gas briefly and causes a current to flow through the tube, which the circuitry on the board detects. And then this is the microcontroller, this little white board that piggybacks on the main board. It is going to have the software that runs this little organic LED display. And you can see, maybe if you can read it at the top, it's counting 12 counts per minute is the number of discharges that it measured in this tube in the last minute. And then it also calculates the radiation level based on that in the units called microsieverts. So this is this processor is a member of the same family as the little board that I held up at the beginning of this talk. So it's what I did with this is the person who designed the board, I convinced him that I wasn't going to try to steal his design, and it took a couple of emails to convince him that I was legitimate, but then he sent me his software and then I modified it. And so then through these wires, the black and the white and this brown wire, in this little box, I should have taken it out of the box for the purpose of this picture. I have a little bare board GPS module. And so I modified his software to once a minute read the latitude and longitude from the GPS as well as the current time. And so then it can tag each radiation reading with the location and the time and the date. One of the features of this little board is, if you can notice the squiggly line here at the bottom, that is a Wi-Fi antenna. So this little board contains Wi-Fi, and it then uploads my radiation readings along with the time and the location to the internet. And I can drive around with this in my car and generate a map of radiation readings as I drive on the roads here in New Jersey. So that's just a little example of something that I put together. So let me talk about the board that I'm going to demonstrate today. So it uses a processor called the ESP8266. And this is an example listing from the internet. And this is a typical cost that these go for. They're around $4 and then a couple dollars. This one had, I guess, free shipping at the time I took this snapshot. Well, that's with larger orders. Typically shipping from China nowadays is a couple of dollars. So if you order more than one, you can amortize the shipping. So the neat thing about these boards is it's a complete development system all in one. So basically you plug into this little micro USB connector and you're done. Your laptop or desktop computer plugs into here, and it has this little chip nearest to the USB connector is what's called a USB to UART bridge. So it converts the USB to a serial interface to the microcontroller itself. It has a power regulator built in, so it takes the USB power and converts it to the voltages needed on the board. So this is a complete development environment, and you don't need any other hardware than this. All you need to do is plug a micro USB cable into it, and you can start developing. So what is the ESP8266? So this is a really popular microcontroller, and it first came to the world's attention in 2014. And or it came to the Western world's attention, because it was initially developed in China, and initially all of the documentation was in Chinese. But then this third-party manufacturer, called AI Thinker, put it together into a ready-to-use module. So they took the chip and combined it onto a little board and started to create some English documentation. And it just took off like wildfire, because at the time there was nothing that was anywhere close to this price, sub $10, including Wi-Fi, RAM, ROM, the processor, a complete system for less than 10 bucks. And then there's another successor to this called the ESP32, which was released several years later, and I'll talk about it in a couple of slides. So what's in this processor? So it's, compared to your desktop, it's modest. It has a relatively small amount of RAM memory, just a couple hundred kilobytes, but it has a fairly decent amount of ROM. The little board that I showed you has 4 megabytes, and that's pretty typical. So there's quite a bit of ROM storage, so you can have a fairly significant program in it. And then it has the Wi-Fi, both BG and N, so it'll do the 2.5 gigahertz, 2.4 gigahertz Wi-Fi. It does not do 5 gigahertz. And it has a bunch of digital I/O, so it has 16 individual general purpose pins, and then it has, let me go back a page, and then it has several serial digital interfaces. It also has a 10-bit analog to digital converter for reading voltages. So one of the places, these little chips are embedded in a lot of things. So if you have a smart home, you may be using these Wi-Fi smart switches from a little company called Sonoff, because they're really inexpensive and a lot of hobbyists use them. And they all are based on the 8266 chip. And this is a typical one, again, from you can order them from China, and $4.50 for this one. So this is a way to, via Wi-Fi, control 120 volt appliance. Okay, so the next generation chip was the ESP32. It's this particular board that I snapshotted was $8, and with, again, shipping of about $2.50. Has the same basic features, so it's got a complete development environment. You don't need anything else other than a USB cable to start developing with it. And it's a lot more powerful. So you notice the processor runs at 160 or 240 megahertz versus the 80 megahertz that the first generation did. Has a lot more RAM. It's got about half a gigabyte of RAM. In addition to the Wi-Fi, they added Bluetooth. And then it has a number of additional interfaces. So in addition to the analog interface, it now has 18 channels of analog interface. It has 2 analog output. It can handle touch sensors for touch input. And then it has additional serial digital outputs. So there's lots and lots of, the whole kitchen sink is built into this. And then it also can handle driving motors, different kinds of sensors like Hall effect sensors, infrared sensors. You can connect just about anything to this chip. It's really featureful. It has additional security built into it, so it can handle encryption over the Wi-Fi. And then it also has built-in power management, so it can go into low power modes. So if you run this chip off of battery, it can go to sleep, and in deep sleep it pulls almost nothing, 5 microamps. So you could get months of battery life out of one of these chips if they just periodically woke up, took a reading, uploaded the data, and then went back to sleep. So this is a block diagram. I'm not going to go through it, but it just kind of shows you all of the different hardware interfaces that are built into this chip. So with all of those pins that come off of that little board, you can connect just about any common sensor or output device. If you want to drive a servo motor or whatever from this chip, you can do it with these little inexpensive chips. And then the last one I wanted to kind of tease you with, this is something that I have also been working with, is an Internet of Things radio protocol called LoRa. And they have combined the LoRa radio with these ESP32 microcontrollers. And so on a little board like this, you can have a complete development environment to develop Internet of Things that use the LoRa radio. What is the LoRa radio? You may or may not have noticed, but Amazon, about a month or so ago, introduced a bunch of new hardware products. So new versions of the Amazon Echo, new versions of their Ring products, the cameras and the doorbell and whatnot. And built into some of those products is a LoRa radio. And so Amazon has in the works, we'll see if they actually follow through with it, but they're starting to build an infrastructure with these LoRa radios. And the neat thing about LoRa is it has a long range. That's what LoRa, the name came from, is with even a simple antenna like this, these little radios have a range of like a half a mile or a mile. And so the idea of Amazon is if enough people get these in their homes, then they can sell like a LoRa dog collar. And if your dog wanders off, Amazon can show you on a map where it roughly is, because if there's enough people with Echo devices or Ring devices in their homes with these LoRa radios, they can track where that dog collar is, which house it's closest to. And you could go and find your dog. Even if it had wandered maybe miles away, it would be picked up by one of the Amazon devices that supports this radio protocol. So that's kind of coming into the future. So these little boards currently sell for around $20. This was this particular one was from Amazon, so it has free shipping. This doesn't come from China. You can get this in 2 days from Amazon. So again, has a display, has the processor, has the LoRa radio and the antenna. Okay, so let me stop sharing the PowerPoint, and instead I am going to give you a live demo then with Arduino. So let me get the drag the Arduino windows over onto my other display, and then I'll share that display. And one more window to move. Okay, so we are, let me do the simple example first. Open recent, and I'm going to open Blink. So this is my Blink demo, and setup is going to, can everybody read this, by the way? I guess somebody say yes or no, or yes. Okay, I just wanted to make sure I was displaying the right screen here and that everybody could see it. So I'm going to put the chat up too. I'll answer the chat question in a moment. So the setup, all it does is it enables the pin, and the pin has a descriptive name, LED, built in. It enables it as an output pin so that we can then turn the LED on and off. And then the loop is going to write a logic low to that pin, and when the pin is a logic low, the LED goes on, because the other side of the LED is connected to the positive voltage. And so when the LED underscore built-in pin goes to a low voltage, then there is 3.3 volts across the LED. So, and then we wait a half a second, then turn the pin high, then there's 3.3 volts across both sides of the LED, so no current flows, and the LED goes off for half a second. So in the user interface up at the top, these left two icons, the first one just compiles so you can see if it compiled correctly, and then the second one compiles and uploads. So that's the one I'm going to do. So I will click the upload button. So it's right now it's compiling. Down here you can maybe make out that it is doing that. I'll enlarge the area at the bottom. So it's counting up right now as it's downloading over the USB cable. It's loading the compiled code into the Arduino, and now it's done. So let's read real quick what happened here. So the first things it did was it printed some statistics on the size of the program segments. So the code in Flash sounds like a lot of code for this very simple program. It's about 1/4 megabyte of code, 228,000 bytes. And that's because it's got an extensive set of libraries that it loads into Flash. And those support things like the Wi-Fi, which I'm not using, and all the other functionality on that board. So there's a huge amount of libraries that go into that 4 megabytes of Flash that are eating up roughly 1/4 megabyte of the Flash. And then of my RAM, you can see there's only about little over 50K of RAM that is in use on this. And then it prints some statistics. It's the USB is mapped to COM3 on my Windows box that I'm developing on. It connects to the board, identifies the chip, that it has Wi-Fi, what the crystal frequency on the board is, what its MAC address for the Wi-Fi interface is, etc. And then it configures the board, compresses the download package, writes the package to the board, and then resets and starts the board running. Okay, so as you can probably see here, the board is flashing. So it's half a second on and half a second off. If your Zoom screen is set up where you can see my headshot and see the board flashing. So let's make a change just so you can see that that I am doing this for real. So I will shrink the bottom part of the window, and let's make it flash faster. So let's make it say 200 milliseconds on, and let's make it 100 milliseconds on and 200 milliseconds off, just for fun. Okay, and so then I just click upload, and that's all I have to do. So it's compiling. There's a little progress bar over here at the right side. It's done compiling, and now it's connecting to the board. Now it's loading the software onto the board, 33%, 50%. I could probably turn the transfer rate up, but I put it at a slow one just so that I would be confident that it was not going to glitch on me today. And now you can see hopefully that it's flashing rapidly. So it's 1/10 of a second on and 2/10 of a second off. Okay, any questions about that? Okay, so before I answer Nabil's question that's in the chat, let me talk briefly about how you would get started with using Arduino. So I'm going to go ahead and launch a web browser. and I'll put it over into this window. And okay, so this is the website, arduino.cc is where the hardware and the software both are. So if I click on software, and you'll notice there's two choices, Arduino Create. I'll show you that one first. And what it is a web-based development platform for Arduino. So you can set your you can do your development in a web browser, and so the user interface looks very similar to the Java-based Arduino IDE. I prefer to use the native IDE, and the way you get to it is you go to software downloads, and that is where you can download the IDE. And so they have packages that are all set up for Windows, and the first two are the regular Windows applications. The one in the middle is if you want to do the so-called modern Windows app that you get from the Microsoft store. So that's this one. I prefer the traditional Windows app that you launch from the start menu. And then they have different ones for Linux and Mac OS. And so you download the Arduino IDE, and then it becomes an application on your computer. So once you've got it downloaded, you go to Tools, and you choose your board. And so when you go to the board selection, initially all you're going to see is Arduino boards. So this is going to be the selection that you have. So if you buy a genuine Arduino or an Arduino clone board, then you could you have everything by default. If you're using a different hardware platform, like I'm using this 8266, then you need to install the software package to support those boards. And the way you do that is under File, Preferences, and this entry here, Additional Board Manager URL. So if you have a different kind of board that supports Arduino, there will be a JSON URL, and you go and just copy paste that URL into this slot in the Preferences menu, and that's all you have to do. And then when you go to Tools, those boards will also show up in the Boards Manager. And so then I get all of these 8266 boards in addition to the Arduino boards. And there are many other types of development boards that also support the Arduino environment. So you can load as many different board managers as you want and work with them. And then under Tools, the other items here that you will probably want to change, the main one is the port, and that is the virtual serial port that your USB maps to. So when you plug the device into your computer, if there's a driver for the chip, and there should be, it should have automatically installed on most systems, it will map to a virtual COM port, a virtual serial port, and so you select which one. And COM1 is built onto my computer motherboard. COM3 is the one that maps to the USB for me. And then the other thing you might want to change is the upload speed, and I have it currently set to 115,000, just to be safe. Before I gave the demo, I tried running it up 10 times that, up around a megabit, and it still seemed to be working, but I just decided to play it safe for this demo and left it at the default at 115,000. But basically, once you've done that, Then the third thing is to write a program, and they've already done that for you. So under File, then you go back to File and Examples, and it turns out there's examples for the, there's the built-in examples which are designed for the Arduino boards, and then there's kind of generic examples which work on any kind of board. And then finally, my board, the my little 8266 board, provided, the people who wrote the Arduino support for it provided a whole bunch of examples to show off, to get you started with development for that board. And so the examples I'm showing you today are all right out of the examples section. I didn't have to write them from scratch. Okay, let me real quick answer the question, and then I'll do my other demo, and then I'll be done except for questions and answers. So the question from Nabil is, I've had this question far too long. Since you worked in the industry for so long, what do companies use for production products? I'm pretty sure they aren't using Arduinos. Like what microcontrollers would our cars be using? So in the industry, for when we're doing product development, it would not be uncommon to use an Arduino for product development because of the fact that they're so ubiquitous and so easy to develop with. So if I wanted to rapidly put together some prototype on my electronic workbench in my job, an Arduino would be a common choice. But if you're going to put it into production and sell hundreds of thousands of them, like the engine controller for a car, that is not what you would do. You would use a specialized microcontroller, and there were just a couple of companies that focus on the automotive industry, if using that as an example, that make dedicated controllers for that end use. So when I showed you on the slides the picture of this ESP32 chip with all of these different peripheral blocks on the chip, the microcontroller manufacturer would make a dedicated chip because the volume is so high. They will build a specialized chip just for that car company with the particular input-output blocks that are needed to control an automotive engine. And then they would also design the chip for the automotive voltage and temperature ranges, because in an automotive environment, it can get quite hot either under the hood or inside of the cabin of a car on a hot day when the windows are rolled up. And so the chips used in automotive uses have to have a very broad temperature range, much more so than normal consumer electronics. And so it's going to be a specialized chip with dedicated I/O capabilities, and the chip itself may have maybe some extra specialized instructions added to the instruction sets. So these are heavily customized chips made just for that end purpose. For when I was developing analytical instruments, our volumes were not so high that we could justify a custom chip. So we would use an off-the-shelf microcontroller chip that we would purchase from one of the semiconductor companies. And so many of those nowadays would be the same ARM architecture that is in your cell phones. For instance, almost all cell phones have an ARM processor, and that same microcontroller instruction set is common in many Internet of Things devices. And in my case, I was developing analytical instruments for chemical analysis, but things like your Nest or Ecobee smart thermostat in your home, or your smart light switches, or your smart light bulbs, or your Roku device, most of those probably have a microcontroller that includes an ARM processor. And then whatever I/O, if it's lower volume, it'll be a commodity chip that has the required IO and maybe some extras that you aren't using, but you pick the closest one you can find that fits your need. If you have really high volume, then you can do a custom chip. Okay, so I hope that answers Nabil's question. So let me show you my other quick demo, and then I'll turn it over to questions. Okay, so this is another one off of the website, and this is it's called a basic HTTP client. So HTTP is the protocol that's used to talk to web servers. And so this is a little bit more complicated example, but you can see that the code, as I'll show you, is maybe, I didn't count the lines. I don't think it's more than 100 lines of code total. So what's setup going to do? It's going to set up the serial port, and it does that so that I can write debugging information out and see what this chip is doing. And so then it's going to print 3 blank lines, and then it's got a little loop that's going to print wait and count down. It's going to say wait 4, wait 3, wait 2, wait 1. So it just does a little countdown so you can see that it's starting up. And then when it counts all the way down, it initializes the Wi-Fi. And it's this simple. The first line, Wi-Fi.mode, Wi-Fi_STA. This configures the Wi-Fi on the board to be a Wi-Fi client. These little chips are capable also of being a Wi-Fi access point. So it can act similar to your wireless router in your house. And so you can have your laptop connect wirelessly directly to one of these chips without needing a wireless network in your home. You can connect directly to the chip. It acts like its own access point if you put it in that mode. In this case, I have an access point in my home, so I configured the chip to be a client. So it's more like your laptop. It's going to connect to my existing access point in my home. And then I give it my credentials. So the SSID is the name of the wireless network that I'm going to connect to, and then pass is the password to my wireless network, and I define those up above. And then the loop, and the loop, let me enlarge my window again. We can probably get the loop, pretty much the whole loop will fit on the screen here. It's actually that small. So this is the whole loop. So it waits to make sure that the Wi-Fi connection has succeeded, and then it's going to print out a begin message. And at that point, it's going to connect to the web through this Wi-Fi connection. And the website that it's going to connect to is this one. And let me copy paste that into my browser. Okay, so this is this simple website that I chose, and I chose it just because it's very simple, so it's not going to send a lot of data back. So this is what it looks like in my browser. It says the connection header, this page will be served to you with the following headers, and then it's got an email address if you want to contact the people who developed this. So this is a little web page that was created for web developers. So I'm going to connect to that development web page. Then I'm going to send it a GET, which, if you know the HTTP protocol, GET means send me that web page. So I sent it, I entered the URL, and then I'm going to send the remote site a GET HTTP GET command and ask for the web page. And so then the page will be retrieved. So this line is going to issue the GET command. And then this line here, GET string, is going to retrieve the web page as a big string. and then it's going to print the web page, all the data that that web server sent back. And then it ends the connection and waits 10 seconds, and then the loop runs again and it gets the web page again. So let me go ahead and compile and upload that. And in the meantime, I'll show you this other screen. So this is the serial window that is also part of Arduino, and the same serial port, virtual serial port through the USB connection that is currently being used to upload the data can then be used by the board to send text back for debugging purposes. So once this starts up, we should see something happen in the window. Okay, so now it's starting, set up wait 3, wait 2, wait 1. Okay, and it did the get command, it retrieved the web page. Now it's waiting 10 seconds and you'll see it retrieve the web page again, and there it goes again. So it's beginning each time it downloads. It's right here is where the download begins, and there's another. So every 10 seconds, it's pulling the page down. So this is what the code of the web page looks like. And in this case, I'm just printing the web page in text form to the serial output so that I can see that it was successfully retrieving that web page. If I wanted to be a web browser, then I would render that in the pretty looking page that I showed you a moment ago in Google Chrome. Okay, so questions. That's pretty much what I wanted to show you. Is it's that simple to, and it's that inexpensive too. For less than $10, you can buy everything you need to do development. And the development, you can end up with a working system that connects via Wi-Fi to your home network, and you could interface sensors to it. You could have it be a web server. You could have it be a media server. There's a million things that people have done with these little boards, and you can put them together for almost nothing. For things like a web server, you don't even need any extra components. You know, everything that's built onto this board is all you would need. Okay, so I have a question here. I have an ESP8266. It gets quite hot when I'm running a web server. Is that normal? Probably not. I'm sitting here and, you know, this chip right now, granted, it's not doing a whole lot, but it's just, I would say, I can barely detect any warmness at all. What I would think might have happened is maybe some of the pins might not be configured correctly. And so you're maybe running a lot of current through an output pin. Another possibility is that your web server code is got a busy loop in it. So rather than blocking and waiting for a client connection, maybe it's just spinning in a circle and rapidly executing all of the time, and generating more heat that way. But it's certainly, you should be able to write an 8266 web server that does not get hot. Other questions? You don't have to do chat. You can always unmute, and I enabled everybody's microphones. So if you want to unmute and ask a question, you're welcome to do that too.
So do all do all examples have like different codes, or at least different like I guess like a JDP, I guess, like a different like call out or how to use specific commands and stuff?
So there's the web interface. You saw that it just took a couple of lines to basically be a full web client. A full web server with the Arduino is similarly just going to be a handful of lines to initialize the web server and accept a request and return what was requested. So that huge amount of code that goes into the ROM that's part of the Arduino library is already written for you, and there's documentation online as well as lots and lots of examples showing the use of those libraries. Like anything else on the web, there's a lot of bad examples out there, and so don't get frustrated if the first one that you work with doesn't work right, because people have uploaded, poorly written code. But there's also, find some code that works well and then build from that, or build directly from the documentation. I don't know if I answered your question or not.
You answered it. I was just wondering if there were being examples. All right, so they're online, not really on the example, like loaded examples.
Yeah. So the examples that are installed with your board manager. So in this case, it was for the Node MCU board manager. That's the name of this little board that I have, that I demoed today. This little $4 board. These are all examples that were written explicitly for Node MCU boards. And again, Node MCU was originally made by a company, but again, it was an open design, and the board that I have is a clone of the original Node MCU, and there's lots and lots of people who have copied that, but they're all written to this, they all use the same pinout and do the same thing, so they should be interchangeable. And so you can see here, there's web server examples. You can create a Wi-Fi mesh network. So they have an example of doing that. Lots of examples using the different ports on the board, serial ports, the servo, if you want to control a hardware motor servo, using touch controls, on and on and on. There's so many I/O options with this little board, and there's examples for how to use them all that are right in this directory. Or you can just search online and find somebody who's done a project similar to what you want to do, and build from that as a starting point. I guess one thing I will mention is, let me contrast this with Raspberry Pi. So Raspberry Pi is more like a desktop computer in a small form factor board. So it runs typically it would be running the Linux operating system. There are several versions of Linux that run on the Raspberry Pi. There's a specialized version of Microsoft Windows that can also run on the Raspberry Pi. But presents more of a standard interface like you would get with a desktop or a laptop computer. And so the development for it is done by logging in. The development is most often done directly on the board, whereas in Arduino, we're doing cross development. I'm developing, in this case, on my Windows PC, and then moving the files onto my little Arduino board. The Raspberry Pi, you develop directly on the Raspberry Pi board. The Raspberry Pi is running a full operating system. My Arduino board, in this case, this little 8266 board, is not running a conventional operating system at all. It's running this specialized little loop that has a reset function and a loop function that repeats over and over again. So there's not a conventional operating system per se on this board. There's basically just a little simple runtime that supports the operation of the code. The advantage of the Arduino board is, because you're running directly on the hardware, though, is you can do things that have real-time response. So if you're controlling a hardware device like a robot, and you want to have the robot respond to a sensor and you want to have it respond quickly, it would be hard to do that with a Raspberry Pi because it's running a conventional operating system, and its responsiveness, it's time sharing between all of these different processes, and it's not going to respond predictably. Whereas an Arduino board, you can get real-time performance. If you need it to respond in microseconds, you can write code that will respond in microseconds, because it's dedicated. It's only doing the code that you put into it. It's not running a general purpose operating system. So the projects that you typically develop with the Arduino are very close to the hardware, and so it's a lower level version of software that you're developing. You can write the code in this C++ like language, or C or C++ like language, but but it's not part of a bigger system. It's, that's all that's running on this board when you start your little program up. The board, you own the board. That's all that's there, and so it's going to be really responsive. Okay, so we've gone almost an hour, so I think that I'm going to stop the share there, and I'm going to officially end this. People can go back and work on their hacks, and if anybody wants to hang around, though, I will stay here as long as you've got questions for me, and I can always share the screen again and show you how to do anything in particular on the Arduino platform. So thank you, and have fun at the hackathon. I'll see some of you tomorrow. I'll be one of the judges, so there's some chance that I'll be judging your projects.